Hello everyone, welcome to the second episode of this series. In this video, we'll talk about elementary operations and augmented matrices. So we want to find a general method to find solutions to a linear system. So, vaguely speaking, the strategy we'll use will involve something called elementary operations to transform our given linear system into an equivalent system whose solutions are easy to find. Now, let's break this down. By equivalent systems, I mean that they have the same set of solutions. And elementary operations involve these three things: exchanging the order of two equations, multiplying one equation by a non-zero number, and adding a multiple of one equation to another one. I do want to say that the addition of an equation to the other one up to a multiple is the most useful one, and exchanging two equations is perhaps the least useful one among these three. So let's start with an exercise. So we're given this system of linear equations in three variables x, y, and z. Now I know that the last equation only has y and z, but we can treat it as a system of linear equations in variables x, y, and z, where the coefficient of x is 0 in the last equation. So we'll use these three elementary operations, mostly the second and the third one, to find a solution to the system. Okay, so we're given these three equations. We'll call them equations 1, 2, and 3. The first thing we want to do is we multiply the first equation by -1 and we add it to the second equation. So I multiplied x plus y plus z equal to 3 by -1. That gives me this equation here, and I added it to x plus y plus 2 z equal to 4. When you actually add it, you get z equal to 1. And then we can take z equal to 1 and we can plug it in the third equation because it's the easiest one to solve because there's only one extra variable. And we want to find the value of y. So we plug in z equal to 1, and that gives us y plus 2 equal to 2, and therefore y equals to 0. So far we have z equal to 1 and y equal to 0. Now we use the values of y and z and plug them in the first equation or the second one if you want. They're supposed to give us the same answer. So when we plug in 0 and 1 in the first one, we get x equal to 2. So far, when x is 2, y is 0, and z is 1, like x, y, and z satisfy the system of linear equations. So let's verify for the sake of our sanity. So if we plug in x equal to 2, y equal to 0, and z equal to 1 in all the three equations, we get that the equations are satisfied. 2 plus 0 plus 1 is indeed 3, 2 plus 0 plus 2 is indeed 4, and 0 plus 2 is indeed 2. So crudely speaking, this is what the strategy for solving linear system looks like. We first eliminate variables by adding multiples of one equation to the other. And then once we have the value of a variable, we substitute back into the other equations, and we call it back substitution. So this is a very neat idea, but in the next episode, we'll actually streamline it to make it an algorithm. And of course, this strategy as of now doesn't yet work with multiple solutions and no solutions, but we'll see how it does in the near future. Okay, so we want to save time, we want to save notation and space. And for that, I want to introduce this idea of augmented matrices. Because when we're working with the system of linear equations and we're using elementary operations, the only thing we need to keep track of is the coefficients and the constants. The variables themselves are not changing at any point. We do this with the help of an augmented matrix. So we put the numbers in a grid, put brackets around it, and add a vertical line between the coefficients and the constants. For example, if I have a system of linear equations given by these three equations on the left, we can just take the value of all the coefficients and the constant term, plug them in this manner. So 1, 2, 3, and 4, 5, 6, 7, and 8, 9, 10, 11, and 12, and then put this vertical line just to separate out all the coefficients on one side and the constant term on the other. So for elementary operations on linear systems become elementary row operations on augmented matrices, and the three elementary row operations on the augmented matrix are essentially exchanging two rows instead of two equations, multiplying one row by a non-zero number instead of multiplying one equation, and adding a multiple of one row to another row instead of adding a multiple of one equation to another equation. So to understand this, we're going to solve this exercise. So we're given this system of linear equation that we saw on the last page, and we want to convert the system into an augmented matrix, use elementary row operations to simplify it, and then determine the solutions to the system. Okay, so we're basically going to break this into three steps. The first step would be to convert the linear system into an augmented matrix, and that's something we saw like a couple moments ago. So we just take the coefficients and the constant terms and put them in this matrix structure, and we put a vertical line to separate out my coefficients and my constant terms. Our second step would be to use elementary row operations to simplify the augmented matrix. So for example, we'll first start by adding -5 times row 1 to row 2 and -9 times row 1 to row 3. The reason we're doing it is because by doing that, we eliminate the first term in both row 2 and row 3, making these two equations a little simpler than before. And that's the gist of it. That's what we are heading towards. So we're multiplying 1, 2, 3, and 4 by -5, and then adding it to 5, 6, 7, and 8 respectively. So we get 5 minus 5, 6 minus 10, 7 minus 15, and 8 minus 20. So we get 0, -4, -8, and -12. And similarly, we multiply 1, 2, 3, and 4 by -9, and we get 9, 18, 27, and 36. And we add it to this last row. So we get 0, -8, -16, and -24. Then we add -2 times row 2 to row 3. And the idea behind it is very simple, that we want to make one of the equations simpler. But in this case, when we multiply row 2 with -2 and add it to row 3 ends up being cancelled. And then we multiply row 2 with -1/4, because all three of the terms, actually all four of the terms in row 2 are multiples of -4. So when we do so, we get 0, 1, 2, and 3. Now, step 3 is to convert the simplified matrix back to a linear system and determine the solution of this new system. So we just take these entries and just convert them into equations. So 1, 2, and 3 become coefficients of x, y, and z. So x, 2y, and 3z equal to 4, because that's the constant term. We get 0x plus y plus 2z equal to 3. And the last equation is just redundant, but I've written here for the sake of completeness. Now, this linear system is equivalent to the original system and much easier to solve. From the second equation, we can write y equal to 3 minus 2z and substitute for y in the first equation. So we get x plus 2 times 3 minus 2z plus 3z equal to 4, or equivalently x equal to z minus 2. Now, therefore, the infinite set of solutions is the set of triples t minus 2, 3 minus 2t, t for all real values t. Remember, we call our t the parameter. So what we've done in the first two episodes is we defined a general problem. We provided tools for simplifying that problem. We gave a vague strategy to solve the problem, and we introduced a time-saving notation as well. Now, next time, we're going to answer the following questions. When is a system of linear equations easy to solve? how can we decide which elementary row operation to use, and how can we tell if we have no solutions or multiple solutions. And we did introduce matrices today, but not in a proper way. So for now, just treat them as very formal spaces to store numbers like a grid or a spreadsheet. And with this, I would like to end the second episode. I will see you guys soon. Until then, happy learning.